Hello, today we're going to cover a method called the reduction of order. And the basic idea behind this method is that we're going to reduce a second order differential equation down to a first order equation using a substitution. After this section, we'll learn methods that allow us to actually deal with second order and higher order differential equations. But this method is actually very useful because it's going to show us how to handle the situations where we have two solutions to a second order differential equation, but they appear to be the same solution. And reduction of order tells us what to do in order to fix that. Okay. So because the solutions of a second order differential equation are linearly independent, we know that if we were to look at the ratio of the two solutions, we would get some non-constant fraction. So here's what we're saying. y2 and y1, they are linearly independent. So if we divide y2 by y1, we won't just be left with a constant. We'll be left with some function u of x. And then we could solve for y2 and see that y2 is equal to y1 time some u of x, where u of x is unknown and it shall be found by using this substitution. So we're going to walk through this process. I've got the substitutions that we're going to use, and then we're going to put them into practice. Okay. So the formal substitution is that we are going to let y equal y1 times u. Then we're going to find y prime, given that y1 and u are both functions of x. So y prime will require us to use a product rule on y1 and u. Then we will also have to find y double prime. And it's a bit ugly, but it's just two product rules. In theory, you might think we just memorize these y prime and y double prime forms, but in reality, we just take derivatives, okay? Once we have found these values, y prime, and y double prime, we will substitute them into the differential equation. We will reorganize everything, get everything in nice and neat and clean up and, combine like terms, all the things. And then we'll need a second substitution. And the second substitution will be that w is going to replace all the u primes, and w prime is going to replace all the u double primes. And then our problem will be a first order differential equation that we can solve. All right, let's go through a specific problem. I chose this problem because it has this equals e to the x. And so the method I'm going to teach you actually is the only reduction of order method that works when we have a non-homogeneous term on the right-hand side of the equal sign. For the homogeneous equations, we'll have a formula we can use. So I'm going to show you the hard way first because you will need this for some problems, any of them that have a non-zero g of x, but you will use the formula for the others. Okay, let's do this. We are told to use reduction of order to find a second solution, y2, when we have y double prime minus 4y prime plus 3y is equal to x. We're told that y1 is equal to e to the x, which is great. Okay, let's try this. So we are going to first let y equal e to the x times u. Right? So that's using y1 times u. Remember, u is not just a variable, it's u of x. Okay? Then y prime is equal to the derivative of the product rule here. So we'll get e to the x u plus e to the x u prime. Okay? And now we need y double prime. So we'll focus on the first term first. The derivative of e to the xu is e to the xu plus e to the xu prime. Then we'll take the derivative of e to the xu prime. We get plus e to the xu prime plus e to the xu double prime. And y double prime simplifies. It becomes e to the xu plus 2e to the xu prime plus e to the xu double prime. Okay, next thing we're going to do is substitute these into the differential equation. So the y double prime minus 4y prime plus 3y is equal to e to the xu plus 2e to the xu prime plus e to the xu double prime. That's for the y double prime. Minus 4y prime, that's going to give us minus 4e to the xu minus 4e to the xu prime. And then plus 3y will give us plus 3e to the xu. And then this is all equal to x. So we need to combine some like terms, see what we can do to make this look a little bit better. I'm going to rewrite this so that all of my, well, let's see. I'm going to rewrite this so that I've got my u double primes written first. So this becomes e to the x u prime. Okay, so that term's done. My u prime terms, I've got a 2e to the x u prime minus a 4e to the x u prime. So that's going to give me minus 2e to the x u prime. And then it looks like I have 1e to the xu, 3e to the xu, that's 4 of them, but then minus 4e to the xu. So nothing's left from that. And this is all equal to x. Okay. The next thing is that this is now completely simplified and there's nothing more we can do to it. It is still a second order differential equation. So at this point, we're going to do our second substitution. We're going to let w equal u prime and w prime will equal u double prime. Okay? And so what we get is e to the x w prime minus 2e to the x w is equal to x. I forgot to write, and substitute into the differential equation. Okay, so it's substituted in. This is a first order linear equation. We need to get it into standard form. So that's what we'll do. Remember, standard form means that the highest order derivative, w prime, will stand alone. We cannot have that e to the x there. So we'll multiply an e to the minus x through to everything. This becomes w prime minus 2w equals x e to the minus x. And then we need to get our integrating factor. So p of x is equal to a negative 2, and mu of x is equal to e to the integral of minus 2 dx, which is equal to e to the minus 2x. Okay, we're going to multiply mu of x equals e to the minus 2x to the differential equation. So we have e to the minus 2x w prime minus 2e to the minus 2x w is equal to, and when I multiply that through to the third term, I get x e to the minus 3x. Okay, now we need to recognize that the two terms on the left are the result of having taken a product rule on e to the minus 2xw. So in our next step, we'll set up our integral. And then solve. So we have on the left d dx of e to the minus 2xw. We're going to integrate with respect to x. This is equal to the right-hand side integrating x e to the minus 3x dx. Okay. Now on the left-hand side, we have the fundamental theorem of calculus, of course, which tells us that the integral of the derivative, those two undo each other and leave behind the argument, e to the minus 2xw. And on the right-hand side, we have a u substitution, not a u sub, we have an integration by parts. So we need to take care of that. And we should probably let u equal x and dv equal e to the minus 3x. Then du is dx and v is a minus 1/3 e to the minus 3x. We need uv minus the integral of v du. And so that's going to give us a negative 1/3 x e to the minus 3x minus a negative, so it'll be plus 1/3 the integral e to the minus 3x dx. And so one more integration on that, I get a negative 1/3 x e to the minus 3x minus 1/9 e to the minus 3x. Okay, so back into my work. My result on the right hand side is a negative 1/3 x e to the minus 3x minus 1/9 e to the minus 3x plus c. And then the next thing I need to do is I need to multiply both sides by the e to the minus 2x. And finally, what I get is w is equal to a negative 1/3 x. And I'm multiplying everything by an e to the positive 2x. And so that's going to change all my powers of e to an e to the minus x, and the minus 1/9 e to the minus x, and then plus c e to the 2x. Okay, now we need to remember something. W is equal to u prime. So I'm not done yet. So that means u is going to be equal to the integral of w dx. So I have to integrate again. This negative 1/3 x e to the minus x minus 1/9 e to the minus x plus c e to the 2x dx. So there's a lot of integrating that has to happen here. The next thing is that I need to do another integration by parts on one of the terms here, not all of them. It's just this first term right here, the negative 1/3 x e to the minus x. That needs an integration by parts, whereas the other two are direct integration. So I'm going to set myself up again. And I'm going to bring that 1/3 with me. I'm using u and v's in my integration by parts. Please do not confuse those with the u that this function is equal to, okay? This is more just out of habit here. Normally, if I'm using u's in a problem, then in an integration by parts, I use w's instead, but I've got w's in this problem too, so it doesn't matter what I use. I just need to stay consistent in my head. So u is going to be the negative 1/3 x. dv will be the e to the minus x. U is a negative 1/3 dx, and v, sorry, that was du, and v is equal to a negative e to the minus x. So the uv gives us 1/3 x e to the minus x, minus v du will be triple negative, so it's still minus 1/3 the integral e to the minus x dx. One more integration, this is 1/3 x e to the minus x plus 1/3 e to the minus x. Okay, finally, u of x is equal to a 1/3 x e to the minus x plus a 1/3 e to the minus x. That's just from the integration by parts. Now, the antiderivative of negative 1/9 e to the minus x will be a positive 1/9 e to the minus x. And the antiderivative of c e to the 2x will be plus c over 2 e to the 2x. And then we also get a plus d. Now the c over 2, I mean, technically we could just write that as c. It doesn't much matter. I'm going to leave it as is for now. However, we're not done yet. We have another step. 8. So remember, or recall, y is equal to e to the x times u of x. Okay, so I'm going to take this one last step and say y of x is equal to, and I'm going to multiply an e to the x through everything here. I get a 1/3 x plus a 1/3 plus a 1/9 plus a c over 2e to the 3x plus a d e to the x. Okay, I could write that out one more time if I wanted to add the 1/3 and the 9 and the 1/9, but that's just a 4/9 right there. So it's 1/3 x plus 4/9 plus c over 2 e to the 3x plus d e to the x. Okay, so what happened here is I got the full general solution. So we got the full general solution. So I want us to identify all the parts that are in here. The 1/3 x plus the 4/9, that is coming from the particular solution. It is the result of having solved the non-homogeneous equation with that equals x on the right-hand side of the equal sign for our differential equation. The d e to the x, well, they told us that e to the x was y1, so this is our y1. Having a constant in front of it, the d in front of it, that's just because we don't have an initial condition, so we should have an unknown there. And then c over 2 e to the 3x, that's the new one there. It has a constant in front of it, so that's how I know that it's not part of the particular solution. It's actually part of the complementary solution, and that will be our second solution. Okay, so if you are asked to do one of these problems in WebAssign, it may ask you which part of your solution is the particular solution, which part of your solution is the second y, and here's how we figure it out. Okay. So this is admittedly the harder way to work through these problems, but it is the only way if we have a non-homogeneous equation. In the cases where we have a homogeneous equation, things are much more simple. Although you might not agree. I find they're simple because it's just one formula that we need to go through, but it's an integral, and the integral can be difficult, and if you lose a minus sign, you're done. It doesn't work. So let's see what I mean. If we have a second order differential equation in the form y double prime plus p of x y prime plus y equals 0, notice the form there, okay? P of x is now in front of y prime. We are not looking at an integrating factor here. We are just identifying as P of x being the term or the factor that is in front of y prime, okay? And we need it there because we need to be able to identify P of x, okay? So this second order differential equation will have a given solution. We'll be told what y1 is. And then a second solution can be found using this form here. y2 will be y1 times an integral, and in that integral, there's a fraction. The numerator has e raised to a negative integral of p of x dx. So you see what I mean by the signs? In this form, there is a negative. If p of x is also negative, you now have a double negative. If p of x is positive, then we just have a negative, okay? In the bottom of that fraction is the first solution, y1 squared, and then we have a dx. The y1 that is outside of the integral cannot simplify with the y1 squared that is inside of the integral. Those are totally separate. We got to integrate what's inside, okay? So let's apply this to a problem and see how we do. We're going to use the formula for the reduction of order to solve the given differential equation with one solution given. So we're told y1 is x squared cosine of ln of x. Our differential equation is x squared y double prime minus 3xy prime plus 5y equals 0. So I need to first get into standard form. Standard form just means I need to divide that x squared through the equation. So I get y double prime minus 3 over x plus 5 over x squared is equal to 0. And we have that stipulation that x cannot be 0 now, because otherwise we would have divided by 0. So now we have y prime, it is y double prime, and it is standing alone. And I'm going to identify that p of x is equal to, where I missed writing my y prime and I missed writing my y. I can't believe I didn't write those. Okay, sorry about that. P of x is equal to minus 3 over x. Okay. Then we're going to sub y1 and p of x into the formula. So I'll write it out again. y2 is y1 times the integral. It has a fraction in it. The numerator is e to the negative integral of p of x dx. The denominator has y1 squared and then dx. So let's put everything in. y1 is x squared cosine of ln of x times the integral. In the numerator, we have e to the negative of negative 3 over x, so that becomes positive 3 over x dx. In the denominator, everything in y1 gets squared, so it becomes x to the 4th cosine squared of ln of x, and then we have a dx. Okay, so we got to first take the integral in the numerator, and that becomes, we've got the x squared cosine of ln of x times the integral. The antiderivative of 3 over x is 3 ln of x, the absolute value of x. So we get e to the 3 ln of the absolute value of x over x to the 4th cosine squared of ln of x dx. Now that 3 times the ln of x, that 3 needs to become a power for ln of x so that the e and the ln can undo each other. So let's just note this. E to the 3 ln of the absolute value of x is e to the ln of the absolute value of x cubed is equal to x cubed. Okay, so let's simplify with that. This becomes x squared cosine of ln of x times the integral of x cubed over x to the 4th cosine squared of ln of x dx. And then the x cubed and the x to the 4th simplify, and you absolutely have to take care of that. Otherwise, we won't be able to solve this. So I still have the x squared cosine of ln of x outside. My integral now is 1 over x cosine squared of ln of x dx. Okay, now this might be one of the hardest u subs you've ever seen before. Okay, it's not obvious to most people, okay? But what I'm seeing here is I have a 1 over x and I have an ln of x in here. And I know that if u is equal to ln of x, then du is equal to 1 over x dx. So I'm going to try a u sub, okay? A u sub here would lead to, well, the 1 over x dx is just replaced by a du, and then I have cosine squared of u. So this simplifies to the integral of secant squared of u du. And the antiderivative of secant squared is tangent of u. Okay, so now I can go back to my work. I still have the x squared, the cosine of ln of x, but my antiderivative is tangent of ln of x. And I have a plus c. I'm not really worried about a plus c, but I'll go ahead and put it. Okay. The cosine of Lx and the tangent of ln of x, those simplify because tangent is sine over cosine, so the cosines will divide out. And I'm going to be left with x squared sine of ln of x plus c. And what this is telling me is that y2 is equal to x squared sine of ln of x, which is what we're after. The last thing that we could do that we're not asked to do, because they just say to solve the given differential equation with one solution given, and I think it might be smart of us to do this, is to say that the general solution is y equals c1 x squared cosine of ln of x, that's from y1, plus, oops, I did a c1, c2 x squared sine of an ln of x. And that's it. So the process is the same for both methods. Remember the first one I showed that was much longer and required 2 substitutions is required to be used if you have a non-homogeneous term. But if you don't, if you're just dealing with a homogeneous function or a differential equation, then you're going to use this second problem as your guide. Okay? I will warn you that these often result in some really weird U substitutions. You just got to be a little bit creative in your thinking. And that's all I have. If you have any questions, please reach out.